Yeah, I have told you no crystal is 100% perfect. No crystal is 100% perfect. Okay, every crystal has some defect. Okay? Every crystal, right, has some defect. There should be some defect. Okay. What are the different types of defects that actually present, okay, in a crystal? Right? Different types of crystal defects. Types of crystal defects. In crystals, we have line defect, we have plane defect, we also have what is called point defect. Okay, right? In crystals, we have three different types of defect. Line defect means if the one-dimensional arrangement of atoms or particles in a crystal, okay, if they orient, right, if the suppose if the atoms orient like this, it is called perfect arrangement. Sometime what will happen, the arrangement may go like this. It may go like this. Okay, so you may not get a perfect path, perfect straight line. I can say in this way. This type of defects is what we call as line defect. What is meant by plane? Sometimes the 2D layers may not be perfect. Okay, there may be some defect in the 2D layer. Therefore, you'll get a defect called plane defect. What we are going to focus here is about the point defect. Point defect arises due to missing of positions. Okay, that should be occupied by the atoms, missing of positions, or it may arises due to dislocation of particles. Dislocation of constituent particles. So point defects arises due to the missing of particles in crystal lattice, or it may arises due to the dislocation of particles in the crystal lattice. Okay, so if missing of particles or dislocation of particles introduces defects, we call those defects as point defect. So keep this in mind. Point defect arises mainly due to the particles, right? If particle missing its perfect location, or particles as dislocate and occupy some other position in the crystal, okay, we call those defects as point defects, right? Here we are going to focus mainly on point defect. Okay, now in point defect we classify point defects into three. Let me write here. Point defect. We classify point defect into three. Okay, there are three types. We classify like this. Number one, stoichiometric defects. Stoichiometric defect. Number two, non-stoichiometric defect. Non-stoichiometric defect. Number three, impurity defect. Impurity defect. Okay, in point defect, we have these three types: stoichiometric defect, non-stoichiometric defect, and impurity defect. What is meant by stoichiometric defect? Listen, due to the defect, okay, I told you defect arises very specifically we are going to focus on point defect. In the point defect arises due to the missing of particles to the respective position, or due to the dislocation of particles. Okay, so because of the defect or due to the defect, if the formula of the crystal remains same, students listen, even after the defect, if the formula of the crystal doesn't change, we call those defects as stoichiometric defect. So in stoichiometric defect, formula of the crystal or formula of the compound does not change. That's the meaning. It's called stoichiometric defect. Formula of the compound which forms the crystal does not change. What is non-stoichiometric defect? It's very clear. Because of the defect, okay, if the formula of the crystal changes, right? So here formula changes. Okay, due to the defect, if the formula of the crystal changes, we call those defects as non-stoichiometric defect. Okay, what is impurity defect? In impurity defect, we add some impurity purposefully to the pure crystal and will make the crystal as impure crystal. Okay, this impurity, right, the defect that we make due to the addition of impurity is what we call as impurity defect. Okay, impurity defect will also has considerable effect in the properties of the crystal. Okay, so impurity defect is due to the addition of impurity in the crystal. Okay, you take some pure crystal, add some impurity, you will get what is called impurity defect. Okay, all these three comes under point defects: stoichiometric, non-stoichiometric, and impurity defect. Okay, before going to discuss this defect, okay, let me just introduce the two types of defects which normally arises in these three. Okay, what are the two types of defects? Number one, interstitial defect. The other one is missing of atoms. So first let me introduce interstitial defect. Interstitial defect. See, these three types of defects, okay, actually consist of either interstitial defect, or the other one is defect due to missing of position of atoms. Okay, let me introduce what is that. Before that, we'll see what is interstitial defect. Listen, in interstitial defect, suppose, assume that in a crystal, particles are arranged like this. Okay, this is a regular arrangement of particles. Sometime what will happen? Students, listen carefully. Suppose assume that these are all the particles in a crystal which are arranged in a definite manner. Sometime some particles, suppose, see here, here is one particle supposed to present here. That is the proper position. But during the formation of crystal, some particle may not occupy its right position. Instead, it will occupy a position, okay, in between the other particles. We call this position as interstitial position. Interstitial position, right? So, if any particle occupy interstitial position, then the defect arises because of this is what we call as interstitial defect. Okay, so the particle, instead of occupying its actual position, it will occupy some other position in the crystal. Okay, this type of defect is called interstitial defect. Okay, this is one, and second one is called vacancy defect. What is vacancy defect? If during suppose during the formation of a crystal, if some atoms missing its actual position, okay, if it misses actual position, then that place become vacant. Okay, it is called vacancy defect. Say for example, assume that I have a crystal where the particles are occupying its actual positions. These are all positions. Now listen here. See, at this location, some particles supposed to present, some particles supposed to occupy here, but during the formation of crystal, sometime, okay, some positions may not be occupied by particles. Okay, those places appear as vacant position. Okay, if vacant positions or vacant space, vacant points exist, right, in crystal, we call this defect as vacancy defect. Okay, so this is called vacancy defect, and this one is called interstitial defect. Right, these two defects, right, are the common defects or common point defects. These common point defects are present, right, in all these three: stoichiometric, non-stoichiometric, and entropy. So first of all, you just remember what is meant by vacancy defect and what is meant by interstitial defect. Okay. Then another important point: whenever vacancy defect arises, see, this position is vacant. Okay, whenever vacancy defect arises, density of the crystal decreases. Okay, there is a decrease in density. Whereas whenever interstitial defect arises, okay, this atom is not, it is not moving out of crystal, right? It is there in the crystal, but occupying some interstitial position, that's all. So here, density of the crystal practically remains same. Density of the crystal, okay, remains same. Remains same practically. Remains same. It does not change. This point you should keep in mind. Okay, so these two are common defects: vacancy and interstitial defect. These two defects are present in these three types: stoichiometric, non-stoichiometric, and entropy. Okay, and this point you should keep in mind. In interstitial defect, density does not change, okay, appreciably, or I can say practically density remains same. Whereas in vacancy defect, okay, density decreases. Right, now we'll start stoichiometric defect. Okay, so what is stoichiometric defect? Yeah, now we'll start. It's called stoichiometric defect. I have told you, in stoichiometric defect, formula of the crystal does not change due to the defect. Formula remains same. Okay. In stoichiometric defect, we have mainly we have two types. Okay. And here I am going to focus mainly on ionic crystals. So we are going to focus on ionic crystals. So I am going to discuss all these point defects by taking ionic crystals as example. Okay, I am not going to discuss other type of crystal, covalent crystal, metallic crystals and all. Okay, I am going to focus only on ionic crystals. Right? In the case of ionic crystals, okay, there are two stoichiometric defects exist. Right? What are the two types of stoichiometric defects? Okay, in stoichiometric defect, okay, if you take ionic crystals, there are two types. There are two types of stoichiometric defects. Number one, what is called Schottky defect. Schottky, S-H-O-T-T-K-Y. Schottky defect. Number two, Frontal defect. Frontal defect. So in ionic crystals, we have two types of defects, stoichiometric defects. One is Schottky defect, the other one is Frontal defect. Okay. Now, what is Schottky defect? We will discuss Schottky defect first. Schottky defect. This defect, Schottky defect, arises. Schottky defect arises in ionic crystals due to missing of pair of ions, due to missing of pair of ions. Okay, pair of ions having same valency or equal valency. Okay, let me write like this. Schottky defect arises due to missing of pair of ions. Pair of ions means cation and anion. Okay, cation and anion. If a cation missing the lattice, crystal lattice, and anion also will miss the lattice. That's the meaning. Okay, there is a pair of ions missing, right, from the crystal lattice. Okay, so Schottky defect arises due to missing of pair of ions from the crystal or in the crystal. Okay, right? What is meant by that? Listen, suppose I'll take I'll give some example first. Listen, this Schottky defect usually observed in crystals like sodium chloride, potassium chloride, potassium bromide, then silver bromide, etc. Schottky defect usually observed, right, in some of these ionic crystals. Okay, I have given few examples here. Now, what is meant by Schottky defect? Let me show with sodium chloride as an example. Okay, I am not going to draw the actual crystal structure of sodium chloride. Just for understanding purpose, I'll show you like this. See, we have sodium ion, chloride ion, sodium ion, chloride ion. So this is how the crystal is arranged. In crystals, the particles are arranged. Chloride ion, then sodium ion, chloride ion, sodium ion, chloride ion, sodium ion. Then here sodium ion, chloride ion, sodium ion, and sodium ion, chloride ion, like that. Students, observe this carefully. It's a very simple one. Yeah. See, this is a crystal actually. I have taken sodium chloride as example. So in sodium chloride crystal, sodium ion and chloride ions are present in adjacent position. Okay, it will occupy adjacent position. Now see here, while forming the crystal, okay, when sodium chloride crystal is formed, listen here, see, there is a vacancy. Which ion is missing here, students? Which ion is missing here? Sodium ion. Okay, sodium ion is missing. Similarly, which ion is missing here? Chloride ion, correct? That's the chloride ion missing the lattice. So, if one sodium ion is missing, one chloride ion is supposed to miss the position. Okay. So there is a pair of sodium ions missing the lattice. Okay. So you may have one pair missing from the lattice, that is a 2 pair, 3 pair, 100 pairs, 1000 pairs. Okay. It depends upon the temperature and the nature of the crystal. Okay. The number of pairs of ions missing depends upon the nature of the crystal and the temperature. Okay. So here I have shown one pair. One pair is missing now, right? But in a crystal, there are many pairs of ions, okay, missing. Okay, therefore you will get a defect. We call that defect as Schottky defect. Okay, so remember, Schottky defect arises whenever pair of ions, here pair of ions that I mean is cation and anion. If pair of ions are missing, right, from the crystal lattice, then we get what is called Schottky defect. Can we call this Schottky defect as vacancy defect, students?
Yes, sir.
Students, can we call this defect as vacancy defect?
Yes, sir.
Yeah, it is. So Schottky defect, actually speaking, Schottky defect, right, is a kind of vacancy defect. Okay, it's a vacancy defect. Whenever vacancy defect arises, what will happen to the density of the crystal, students?
Increases.
Density decreases. Very simple. Okay. Now listen. Sodium ion carry one positive charge. Chloride ion carry one negative charge. So there is an equal valency, right? One positive charge, one negative charge. So vacancies are equal. Now, if one sodium ion is missing, equally one chloride ion is missing from the lattice. Okay. After the defect, is the charge of the crystal remains neutral or not? Suppose only sodium ion is missing, suppose, then what will happen? Chloride number will become high. Okay, therefore your crystal become negatively charged. Or otherwise, if chloride ions are missing, okay, then your crystal may contain excess of sodium ion. So your crystal become positively charged. But now equal number of cation and anions are missing. So what about the charge of the crystal?
Neutral.
Neutral. Yes. So these are all some of the important characteristics of Schottky defect. Let me write to the next page. What are the characteristics of Schottky defects? Characteristics of Schottky defect. Let me put simply SD. Here SD means Schottky defect. Number 1, even after the defect, crystals remain neutral. Okay, crystal remains neutral because equal number of cation and anion are missing. Therefore, crystal remains neutral. Then second point, for this defect to arise, okay, what is the requirement? Right? Is this defect arises in all type of crystals? No. For this defect to arise, okay, coordination number should be high. This defect arises in crystals where coordination number should be high. In the case of sodium chloride, students, listen, in the case of sodium chloride, coordination number is 6:6. For sodium ion 6, for chloride ion 6. So the coordination number is 6:6. 6 coordination is very high coordination. So Schottky defect usually appear in crystals having high coordination number. Then next important point, size of the ions, okay, should be approximately same. Size of cation and anion, which forms the crystal, right? Size of cation and anion should be same, at least approximately, right? Approximately same. Approximately same. Right? Or roughly same, we can say. So crystal remains neutral even after the defect. Coordination number should be high. Okay, then only the crystals will show stoichiometric defect. Size of cation and anion should be same or approximately same. Okay, then next important point, that you should keep in mind is, because of the defect, density of the crystal decreases. Because of the defect, density of the crystal decreases. Okay. These are all some essential points you should keep in mind in Schottky defect. Okay, and remember, Schottky defect is the dominant defect present in most of the ionic crystals. Schottky defect, SD, is the dominant defect. Is the is the dominant defect present in most crystals. Students, keep this in mind. In some crystals, Schottky defect and Frontal defect both may also exist. Okay, don't think you should not keep, you should not say that only one particular defect exists in one crystal. No, in some crystals, okay, mixed defects may also exist. That is Schottky defect, Frontal defect, everything may exist together. Okay, so that is another important point you should keep in mind. Right? So this is some of the important points on Schottky defect. Now we'll discuss about Frontal defect, the next important stoichiometric defect. Students, listen. I told you we are focusing on ionic crystals. In ionic crystals, there are two stoichiometric defects exist. One is Schottky, the other one is Frontal. We discussed Schottky defect. Okay, and these are all the points. Now we'll start what is called the Frontal defect. Okay. So next one, Frontal defect. Frontal defect. Yes, this defect arises due to dislocation of ions. Okay, this defect arises due to dislocation of ions. Okay, usually cation. Right, this defect arises due to dislocation of ions in crystals. Okay. Say for example, okay, first I'll give some examples. Examples include zinc oxide, silver chloride, silver bromide, silver iodide, etc. Okay, these are a few examples for crystals showing Frontal defect. Okay, now let me take, say for example, we'll take silver bromide. In silver bromide, listen, size of silver ion is small compared to the size of bromide ion. Students, listen carefully here. I am going to take silver bromide to understand this. Size of silver ion, Ag plus ion, is small compared to the size of bromide ion. Okay, so in the ionic crystal, in silver bromide crystal, listen, silver ions, smaller silver ions. Let me put silver ion with a positive circle. Positive circle indicate silver ion. All right, I'll write it so that it will be easier. Silver ion, then bromide ion, then silver ion, then bromide ion. So this is how these ions are arranged or exist in the crystal lattice. Okay, then bromide ion, silver ion, bromide ion, silver ion. Okay, and here silver ions, bromide ion, silver ion, bromide, silver, bromide. Like this, these ions are arranged, okay, in a definite order. Okay, and this order exists for long range. Now listen, students, in silver bromide, sometimes silver ions, instead of occupying its proper position, okay, it has to occupy this position actually. One silver ion is supposed to present here, but while forming the crystal, what will happen? Sometimes silver ions, instead of occupying its proper position, it will occupy an interstitial position. See, a silver ion is occupying some interstitial position, right? So in silver bromide, okay, you can see what is called the interstitial defect, right? And this defect is what we call as Frontal defect. So Frontal defect arises due to the dislocation of ion. Ion is dislocated from this position to this position. It is dislocated. If defect arises due to the dislocation of ions in ionic crystal, we call those defect as Frontal defect. Okay. So in Frontal defect, there is an ion at the interstitial position. So it is called interstitial defect, and there is also vacancy. Students, keep this in mind. An ion is occupying interstitial position. So it is called interstitial defect. And there is a vacancy also. So Frontal defect consists of both vacancy defect and interstitial defect. Students, keep this in mind. Let me write in the next page. What are the characteristics of the crystals? Characteristics of Frontal defect. Frontal defect. Number 1. Crystal remains neutral. Crystal remains neutral. Is the crystal remain neutral, students? Is the crystal remain neutral, or is it getting any positive or negative charge?
Neutral, sir.
Okay, see, silver ion, it is not missing from the lattice. Okay, it is simply dislocated, that's all. So silver ion is there in the crystal, therefore the total positive charge and total negative charge of the crystal, okay, remains same. Okay, so the crystal is neutral. Crystal remains neutral. Then second point, crystal remains neutral. Then Frontal defect consists of both vacancy defect and interstitial defect. Frontal defect FD consists of both vacancy defect and interstitial defect. Interstitial defect. Okay. Listen, whenever vacancy defect and interstitial defect both exist, then density of the crystal does not change. Or density of crystal, okay, density remains same. Practically same. Density does not change. Density practically remains same. Okay. Suppose, students, let me ask you a question. Suppose instead of vacancy, if instead of vacancy only interstitial positions are occupied, what will happen to the density? There's no vacancy at all. No vacancy, but ions occupying interstitial position. What will happen to the density of the crystal in that case?
Same.
No, here
Remains the same.
No. Listen, what I'm asking, what I'm saying is, listen. Suppose if this position also contains silver ion, and some more silver ions are occupying interstitial position, what will happen to the density?
Positive charge.
Positive charge. Assume that I have a bromide ion also occupying interstitial position equally, bromide ion also occupying interstitial position. So charge remains neutral. What about the density?
Increases.
Density increases. Students, listen carefully. If only interstitial defect present, density is supposed to increase. But here, when I wrote here, listen, when I wrote this interstitial defect, okay, I told you that this position is interstitial position, okay, and that defect is interstitial defect. But when I gave this presentation, I have given a vacancy here. So due to the presence of vacancy and interstitial defect, the density remains same here. Okay, density remains same. So keep this in mind. If vacancy and interstitial defect both exist together, density remains same. Suppose if only interstitial defect exists, in that case density increases. Okay, so in Schottky defect, in frontal defect, right, we have vacancy, so we have vacancy defect. We also have an interstitial atom, interstitial ion, so we have interstitial defect. Both vacancy defect and interstitial defect both are present. Okay, that's why the density of the crystal remains same. No change in the density. Okay, suppose if only interstitial defect exists, in that case density will increase. Is this clear, students? Okay, keep that in mind. So in this case, density remains same. The next point, to form this Frontal defect, okay, what's the main requirement? The main requirement is coordination number. Coordination number of ions should be low. For Schottky defect, coordination number should be high. But for Frontal defect, for an ionic crystal to show Frontal defect, okay, this is one of the important requirement. Coordination number should be low. Then another important point here, the size of cation and anion, okay, should be different. Size of cation and anion should be different. See, in the Schottky defect, I told you size of cation and anion should be approximately same or almost same, correct? Okay, if sizes are almost same, then you can see predominantly Schottky defect. If sizes are different, cation and anion size are different, then you can see predominantly Frontal defect in crystals. Why I am using the word predominantly? Because in some crystal both the defects may exist. Okay, if both Schottky and Frontal both defect exist, we need to say that, okay, whether Schottky defect is dominant or Frontal defect is dominant. How to identify that? Just see the size of cation and anion. If size of cation and anion are roughly same, okay, then in those crystals Schottky defect will be the dominant defect. Okay, if sizes are different, then Frontal defect is the dominant defect. Is this clear, student? Any doubt? Is this clear?
Yes, sir. Yeah.
Okay. So listen, students. In stoichiometric defect, we have two. One is Schottky defect. The other one is Frontal defect. So when Schottky defect will exist, okay, when Frontal defect will exist, keep all these things in mind. Very, very important. Okay. Then now we'll start the next type of defect called non-stoichiometric defect. What is non-stoichiometric defect, and what are the different types of non-stoichiometric defect exist? So the second category is non-stoichiometric defect. Non-stoichiometric defect. What is meant by non-stoichiometric defect? I have told you already. What is the meaning? Students, what is the meaning for
Formula
non-stoichiometric?
chemical changes.
Non-stoichiometric means formula changes, that's all. Because of the defect, if formula of the crystal changes, okay, you will get a non-stoichiometric crystal. Listen, see for example, see ferrous oxide, the formula of ferrous oxide is FeO. If you write FeO, that means there is no defect or there is no non-stoichiometric defect, we can say. FeO is the formula of ferrous oxide. If you write the formula as FeO, we can say that there is no non-stoichiometric effect, a defect present. Non-stoichiometric defect. Sometimes we write ferrous oxide formula as Fe 0.96O. We will write like this. Sometimes we will write like this, Fe 0.96O. If you write formula like this, that means formula get changed. Whenever formula of the crystal changes, okay, you can say that non-stoichiometric defect exists in the crystal. Is this clear, student? Any doubt? Students, any doubt in this?
No, sir.
All of you turn on your camera. Why don't you stop the camera? Turn on your camera. Yeah. Good. See, in ferrous oxide, if you write ferrous oxide as FeO, that means there is no non-stoichiometric defect. If you write like this, it means some non-stoichiometric defect exists in the crystal. Okay. So, point is this. In non-stoichiometric defect, okay, due to the defect, the formula of the crystal changes. Okay, that's the point. In non-stoichiometric defect, we have three types. There are three types. Okay, number one, metal excess defect. Okay, number two, metal, we have two types, metal excess defect and metal deficiency defect. In non-stoichiometric defect, we have mainly two. One is metal excess defect, the other one is metal deficiency defect. Students, listen, cations are here, listen, in ionic crystals, usually cations are metals. Anions are usually non-metals. Okay, you know it. Cations are metal, anions are non-metals. So, metal excess means cations are excess in number compared to anions. Metal deficiency means cations are less in number compared to anions. Okay, so in metal excess defect, what we mean is the number of cations is more compared to number of anions. That's the meaning. Okay, in metal deficiency defect, number of cations is less compared to number of anions. Students, is this clear? So in non-stoichiometric defect, remember, due to the defect, formula of the crystal changes. Then in non-stoichiometric defect, we have two, metal excess defect, the other one is metal deficiency defect. Okay, then we'll start metal excess defect first. Metal excess defect. Okay, yeah. For this, first let us take alkali metal halides. Alkali metal halides. Student, before that, I forgot to say one information here. Isn't in the Frontal defect and Schottky defect, I just forgot this information. See, in Frontal defect, I have given silver bromide as an example. I'm sorry, in Schottky defect, silver bromide. In Frontal defect also, I gave silver bromide as example. What does this indicate?
It has both the defects.
Yes, Schottky defect and Frontal defect both exist in silver bromide. Not only in silver bromide, in many crystals, if you see, okay, both defects exist. But in some crystal, one defect will be dominant compared to the other one. So based on that, we say that Schottky defect is more in number, Frontal defect is less. Okay, so silver bromide is a nice example in which both defect exist, right? Now, in metal excess defect, first I'll take um, metal excess due to missing of anions. Okay, metal excess due to anion vacancy. I can say due to anion vacancy. If anions are missing, listen student, if anions are missing from the crystal lattice, automatically cation number will increase, correct? Actually, in crystal lattice, cation number, anion number. Suppose if their valencies are same, if cation valency and anion valency are same, then in those crystals, cation numbers, anion numbers should be same. Suppose while forming crystal, some anions are missing to occupy its proper position, then those positions become vacant. If anion position become vacant, automatically cation number will be more compared to anion, correct? We call that defect as metal excess defect. So metal excess defect arises, okay, through two ways. Number one, due to anion vacancy. Okay, for this I'll take alkali metal halides as example. Say for example lithium chloride, sodium chloride, potassium chloride, potassium bromide. Many examples are there. Metal, first I am going to discuss metal excess defect which arises due to anion vacancy. Okay. Suppose you take these metal halides, alkali metal halides, say for example sodium chloride. Students listen, sodium chloride, pure sodium chloride is colorless. Okay, the table salt. Right? In table, you see, if you see the table salt, it is colorless. Okay, or people say that it is white. Listen, actually in chemistry, white means colorless. Okay, so sodium chloride is colorless. Good. Now what I am going to do, you take sodium chloride solid which is colorless. I am going to heat this solid. I am going to heat sodium chloride solid in presence of some alkali metal vapor. Alkali metal vapor. So you take sodium, potassium or any alkali metal and make it in the vapor state. So take sodium chloride crystal and fill up the remaining portion with sodium metal vapor, then heat it. On heating sodium chloride solid in the presence of sodium, in the presence of alkali metal vapor, what will happen? This sodium chloride solid, it remains as sodium chloride only, but what happens is that the color, right, color of the crystal, the colorless become colored, it become yellow. Listen, sodium chloride is actually colorless, but when you heat sodium chloride solid in the presence of sodium vapor, right, the sodium chloride crystal become yellow. Similarly, if you take lithium chloride, crystal solid, this is also colorless. You just heat it in the presence of some alkali metal vapor, sodium metal or potassium metal vapor. What will happen? See, lithium chloride will give you what's called violet color. Violet. Sodium chloride become yellow, lithium chloride become violet, and similarly if you take potassium chloride solid also colorless, and heat it with the sodium vapor, potassium vapor, whatever it is. Okay, sodium vapor, heat it, you will get potassium chloride crystal, right, which is lilac. Lilac. Listen, pure crystal is colorless, but on heating this alkali metal halides in the presence of the alkali metal vapor, okay, you will get color. What is the reason for this color? Okay, the color arises due to the the, uh, the electrons, right? Due to the electrons occupy the anion vacancy, right? Whenever electrons occupy anion vacancy, we call the center as Farby center. Okay, listen. The color. What's the reason for the color? Color is due to what is called F center. Color is due to the formation of F centers. Due to the formation of F centers in system. What is F? F means Farby. It's a German word. Farby means color center. Farby means color center. Okay. Students, listen carefully. Whenever you heat alkali metal halide in the presence of alkali metal vapor, okay, you will get color. You won't get same color. See here, lithium chloride gives violet, potassium chloride gives lilac, and the sodium chloride gives yellow. You'll never get same color. You get different colors. But what's the reason for the color? The color is due to the formation of F centers. Now, what is F center? What is F center? What is F center? F center is nothing but whenever anion vacancy is occupied by electron, right? Anion vacancy occupied by unpaired electron. I'll use the word like this, unpaired electron. We call these centers as Farby centers, F centers. What is meant by this? Listen, I will explain this in the next class. Okay, what is Farby center, how Farby centers are generated, and how different crystals give different color. Okay, we'll discuss that in the next class. Okay.